Great questions. Thank you. Okay, so today's topic is equivalent systems. This is not on the upcoming exam, but it's relevant to what we're doing. And so we have these two rules for equivalency that we'll talk about. And then we need what we're talking about with equivalency. And actually, we've mentioned equivalency before. And it's when we did the resultant force. And so we need to be able to explain the similarities between the support reactions in the original and equivalent system. We'll talk about that. Drawing a picture, super key to draw a picture of the equivalent system given the original system. And then there's really two different ways, two different types of problems that we're going to see. Calculate an equivalent resultant force and its location, or we can replace the original system with an equivalent resultant force and a couple moment at a specified point. So we can either ask you to find the location, or we can tell you where it's going to go, and you have to tell us what the moment, the couple moment, is equal to. So for example, our homework number 1 here, replace all this stuff here with an equivalent resultant force and a couple moment at point B. So that means we're going to take away all these forces and this couple moment right here, this couple moments going like this. I'm going to take those all away and replace it with just stuff over here at point B. This process is basically simplifying the problem down. So instead of having 3 forces in a moment, we can simplify it down to just 1 force and a moment. And this is used all the time in practice. And like, imagine a building that might have hundreds of forces on it. And we simplify that down just to 1 force, and it's equivalent. And so we can do all the rest of our analysis instead of having to figure out like what this force over here, what each of the 100 forces is doing. We can just have that 1 force where it's equivalent. And so we can do all of our analysis with just that 1 force, and it becomes much easier for us. Homework number 2, we're asked to replace all these forces, these 3 forces here. So simplifying the system with the resultant force and a couple moment at point A. So we're just going to apply a couple moment here, but it's going to be equivalent. And we're going to talk about what that means when something is equivalent. This one asks us to replace with an equivalent resultant force and determine where it's located. So it's actually asking us where it's located between A and B. So we need to figure out now where it's located as well. The other ones told us where to put it, right? This one told us to put stuff at A. So we have to watch, those are our 2 different types of problems. Okay, so the third hands-on activity is going to be on equivalent systems. It's my favorite of all the hands-on activities, I think. And so what I've got here is our tension protractors. And if you haven't done the hands-on activities, remember you have until next Thursday, February 18th, to do hands-on number 1 and number 2, and then that'll be the end of availability for those 2. But then we'll start 3 and 4 after exam number 1. So this is our equivalent system here. And actually, let's draw a picture of this for today's topic on equivalent systems. We'll do our notes alongside these pictures. So for equivalent systems, we have our setup here, and we have a tension protractor, and then there's a meter stick that's suspended in between these 2 tension protractors here. And the strings we're basically assuming are going straight up and down. They're really close to straight up and down. And so we found we got 6.5 newtons on this one. And we've got 9.3 newtons on this one over here. And we've got these 2 masses that are suspended. This first mass is about right, let's see, it's about right here or so. And that's, as shown in my picture over here, that's 1 kilogram. So 9.81 newtons, converting it into newtons there. And then I've got a half a kilogram over there at that one, and that one's acting about right there. And this one is 4.905 newtons for that half of a kilogram. And then our distances that I measured the distances here, and like the distance from here all the way out to the 4.905, that's a distance of, and let's call this D2. That's a distance of 61 centimeters. And then we'll call this distance right here D1. And that's a distance of 38.1 centimeters. And then let's also label these forces down here, F1 and F2. So that's F1, and then the 4.905 is what we'll call our F2. And so we have, let's label a couple of points on here. Why don't we call this point over here point A, and then we'll call this point over here point B. And the other piece of information that we have is that the distance from A to B is a total of 76.2 centimeters. So let me get that on the drawing here as well. So that distance all the way, and that's from string to string. So from string to string there is a distance of 76.2 centimeters. And so this is our, this one right here, this is our original system. Now, what we're gonna do with, for our equivalent system, let me grab all this stuff and move it down so I can move it with our pictures here. So what we're gonna do for our equivalent system is we're going to take those two and we're going to replace it with this equivalent system. And in the equivalent system, what I've done is I've taken the masses and I've put them at a spot. So the F1 was originally here. This was the F1 location originally. This was the F2 location originally. And so now, but I've moved them to a spot where I still have 6.5 newtons over here, and I still have 9.3 newtons over there. And so what we're doing with equivalency is we're simplifying it, right? We had two forces in our original system, in our equivalent system now. And so let's draw a picture of our equivalent system. And so what this means is that the support reactions stay the same. That's what it means to have equivalency. And so let's draw again. We have our tension protractor here. We've got our meter stick going across there. Our other tension protractor is here. And we still are going to have 6.5 newtons right here. And we're going to have 9.3 newtons right here with just this FR at some distance, and let's call it X. So we want to know, where do we need to put that? So we really have, in order to get our equivalent system, we really just have two rules for equivalency.
I just want to clarify, the FR is just the two masses added together, correct?
Yeah, and actually it is going to be just the two masses added together, and that's rule number one. Rule number one is that we basically, the applied forces in the original, or can I call it the OG, have to be equal to the applied forces in the equivalent, or EQ. And so yeah, that from rule number one, we know that FR is going to have to be equal to F1 plus F2. So that's our first rule. Our second rule is how we're going to find that distance x. And so we've used this concept before. We've used this equation before. What thing have we done that includes a force and a distance? Let me ask. Yeah, we already, okay, got it in the chat. Yeah, the moment, right? And so the moment from the applied forces, in the OG, oh wait, and it's applied forces, and it can be, so the moment from the applied forces in the OG, yeah, let's do in the OG, about any point, and actually we can pick any point, have to be equal to the moment from the applied forces in the EQ about the same point. So whatever point we pick, we have to stick with it for rule number 2. So rule number 1, we figured out this stuff down here. The FR is equal to F1 plus F2. So that's rule number 1, is how we figured that out. Now, for X, we want to figure out where do we need to apply FR so that we still get the same support reactions. We are usually told in the problem statement where to measure things from. I measured X from A. Now, as soon as we know where we're measuring stuff from, that should tell us where we want to take the moment about. So in this problem, if we're measuring a distance X is measured from A, then we should take the moment about point A. So really rule number 2 is the moment about A of the original has to be equal to the moment about A of the equivalent. And this is our rule number 2. So if we want to take the moment about point A of the original, now remember, this is only for the applied forces. And why do you think I only have to consider the applied forces when I take the moment? Because isn't there a force here at B of 9.3 newtons going up, and there's a force here at A of 6.5 newtons going up? Well, the reason I don't have to worry about the reaction forces, and I'm only focused on the applied forces in both the original and the equivalent, is because for equivalency, don't we need those support reactions to be the same? So they would actually, if we did include support reactions in rule number 2, it's actually fine, but they would cancel each other out. The 9.3 in the original would cancel out with the 9.3 in the equivalent, because that's the whole idea of equivalency. And so let's see, what is the moment about A of the original? Isn't that going to be equal to that F1 times a D1? And actually, let's get some signs on this. This is positive, is counterclockwise, so that means that should be a negative, right? F1 is going in the negative. It's going clockwise, so it's a minus F1 times D1 minus an F2 times a D2. So there's our moment about A of the original. How about our moment about A of the equivalent? That's just equal to a minus FR times X. So I'm just looking at, and that's why one of our learning objectives is to draw that equivalent system, because drawing that equivalent system is just super helpful. It might be kind of simple, but draw it just so you can see it and don't make any little mistakes there. Okay, so if I set these equal to each other, if I set the moment about A of the original equal to the moment about A of the equivalent, I'm going to end up with a minus F1 times D1 minus F2 times D2 is equal to a minus FR times X. And let me rearrange this for X. I'm going to have and I can get rid of all my negative signs as well because they'll all cancel out, right? So F1 D1 plus F2 D2 divided by FR right here is equal to X. Or F1 D1 plus F2 D2 divided by F1 plus F2 is equal to X. This is a special kind of average, right? Isn't this like, if we look back at our pictures, if we think back at these pictures here, right? Isn't this a special kind of average? If I had, if this was 9.8 newtons was right here and I had 4.905 newtons, don't we have to find the kind of a balance point in there between those two forces? And what kind of average is that? It's a special kind of average. Does anybody recognize that? It's not an error, although I could see how it could look like that. Yeah, it's a weighted average, absolutely. So what we just did, which is really cool, is we took moments and we came up with an equation for the weighted average. So there's our two rules. Those are the same two rules that are always going to apply for equivalent systems. So if we plugged in our values for this one, we're going to find we'll have X is equal to a 9.81 times that 38.1 centimeters plus that 4.905 times that had a distance of 61 centimeters, and then divide that by 9.81 plus 4.905. There's our weighted average. And we're going to find that X is equal to 45.73 centimeters. And when I did this, I just guessed and checked at first by moving those two weights around. And then I went through and I calculated it. And I got exactly the same thing. I was within half a centimeter of the actual one. So these equations they're real, right? These moment equations, and we know that also because we see that the equivalent system has the same reaction forces, right? It has those exact same reaction forces on the A tension protractor and the B tension protractor as well. Okay, so that's the type, and that's our process for the problems where they're asked to find where the force needs to go, right? Because we found where the distance X, where that needs to go. The other way that they can do this is they can say replace it with a force and a moment at A. And so you can see here, and this was a little bit more difficult, but I took the 1 kilogram and the 0.5 kilogram, they're actually hiding behind my hand. So I put it right here. So I have the FR is right here. And what I'm doing with my hand is I'm trying to apply the best I can a couple moment. And a couple moment is what? It's two equal and opposite forces, right? So I'm trying to apply a force here going up, a force there going down. If they're equal and opposite, the net force to my system is 0. So I'm not adding any force by applying those two. And so really what we're going to show on that is we're applying a moment there at point A as well, or a couple moments right there at point A. And I'm close to 6.5. It's really hard to do this, but I'm really close to 6.5. So basically I'm still at 6.5 and I'm really close to 9.3. So basically I'm 9.3. But what I'm doing with this demo is showing that, yes, you can still get those same support reactions even with a force and a moment. So let's look at the second way here, or second problem type. Is when we replace it with a force and moment at a specified point. We'll say for point A for this one. And so we're going to have the same original as before, right? Because we're still working on this problem where we're trying to get 6.5 newtons and 9.3 newtons. Same original system as before. And so now, though, our new equivalent system instead of having that FR somewhere at a distance x, what we're going to do is we're going to apply, we have our tension protractors here. We're going to apply FR right here. So same two rules. Even though this is the second type of problem, FR is still going to be equal to F1 plus F2, and that's rule number 1. But now, what do you think would happen in this system if I put FR all the way over here at point A? Do you think I'd really have much of a force, much of a support reaction over here at point B over here? Wouldn't it basically go to 0 if I moved just those forces right there? So now we can get back and also if we took the moment about point A, it wouldn't be the same as it was before. So we're going to add a couple moment here at point A. So that's, and they're telling us, they're going to tell us specifically in the problem, replace the original with a couple moment and force at point A. So we applied rule number 1. Rule number 2 is the same as before, where it's the moment about A in the original has to still be the moment about A in the equivalent. And so if we went back to our moment about A in the original, wasn't that a minus F1 times D1 minus F2 times a D2? And if we plugged in those values there, we'd have a minus 9.81 times 38.1 minus a 4.905 times a 61, and that's going to get us a minus 672.97 Newton centimeters. And so we want to make sure that the moment about A of our equivalent is exactly the same. And so when we take the moment about A of the equivalent, is FR causing any moment about this point A right there? Doesn't the line of action of FR go right through? Right, point A is right here. The line of action goes right through, so it's not causing any tendency to rotate, is it? So our couple moments, though, that is right. That's a pure moment. It's a pure rotation. So the moment about A of our equivalent relative to our positive sign convention is a minus MA. Right? That's the only thing that's causing that moment. Now, regardless of where MA is applied, it's always going to be the same. Okay, so we could apply MA at point B. So that couple moment, anytime we have a couple moment, it just adds into our moment equations or subtracts depending on what direction it's going. And so now we set the moment about A of the original equal to the moment about A of the equivalent. And we're going to find minus 672.97 is equal to a minus MA. So we know that MA just has to be that 672.97 Newton centimeters, and that will get us the same support reaction. So same two rules, even though regardless of what problem type they give us, same two rules, right? We're always going to apply the weighted average basically, and the forces. The forces in the original, we can't change the forces, right? If we change the forces, then it's not equivalent anymore. Or if we change the moment that the forces are creating, then it's not equivalent anymore. So as long as we satisfy those two rules, then we've satisfied equivalency. And actually, even though we've satisfied equivalency for point A in both of these last two examples, equivalency is satisfied for everywhere on that rigid object. Okay. Any questions? One of the, I talked about some real world applications in buildings. Some other real world applications is how about finding the center of gravity of this crane here, right? Couldn't you just take the weighted average of all of those forces right there? And that would tell you, if you took the weighted average, that would tell you where the center of gravity is located. And actually we'll continue working on this kind of stuff as we move on this semester. So just wanted to point that out there. Let's go back up to where we were taking notes here, and let's continue. Let's do an example that's got a little bit more that's going on here. And so we're going to be given an L-shaped rigid object, and we're going to have a force up here of 200 pounds. We're going to have another force at about right there of 100 pounds. And then we also are going to have a couple moment, just this moment that's applied right there at point C. Our M is equal to 50 foot-pounds. And we're given some geometry here, like this angle to the 100. That's a 30-degree angle. The angle for the 200 up here, that's a 60-degree angle. And then we've got some horizontal distances here of 3 feet. Another horizontal distance here of 2 feet. And then we also have a horizontal vertical distance here that's equal to 3 feet. We can call this point at the far left, we'll call that point A. We'll call that point B. This is going to be point C. And then we can call this one up here point D. And so what they ask us to find for this problem is to replace the original system with an equivalent resultant force and specify its location measured from A. And it does say along This is along AC. So it's somewhere along, the problems typically tell us, like, you know, it's somewhere along this line, find where that equivalent resultant force is going to need to be located. So we have forces that are now in more than just one direction, right? The examples we did before, we only had forces going straight down. When we have forces that have X and Y components, I like to start, even before I draw my equivalent system, just figuring out what is my X component of all my forces. So we're going to have a minus 100 times the cosine of 30 plus a 200 times the cosine of 60. So I'm just, if it's going to the left, I'm calling it negative. If it's going to the right, I'm calling it positive. And that gives us a positive 13.4 pounds for FRX. FRY would just be a 100 times the sine of 30 plus a 200 times the sine of 60. And we're going to find that our Y component is equal to 223.21 pounds. Now, our equivalent system, based on the problem, let's draw that, because that is so key. Let's take that and let's just, what are we trying to get to, right? That's our first thing, is make sure that we understand what we want our equivalent system to look like. So there's our rigid object. What they're telling us is to replace all that stuff with just an equivalent resultant force. Now we know where the equivalent resultant force is going, right? It's going in the positive X and it's going in the positive Y. And actually, I'm going to leave it in those X and Y components, because when we take moments, we're going to want to know those X and Y components anyways. And they just told us, hey, you know what? It's somewhere along this line from A to C, right? Along A to C somewhere. I'm just going to put it somewhere on there. I don't know where it's going to go. I'm just going to put it like right here. And so there's our FRY. We know is 223.21. And then we have an FRX that's going to the right, and it's 13.4 pounds. And we want to find, where is that located measured from A. So I'm going to measure my distance from point A there. So haven't we effectively already done rule 1? Right? This stuff up here, this was really, that was our rule number 1. Just adding up the forces. Adding up the X forces, adding up the Y forces, and then we drew the equivalent system. And now we can go into rule number 2, is that we're going to have to say, well, the moment about A in the original is equal to the moment about A in the equivalent. And so if we look, the moment about A in the original relative to our positive sign convention, let's go back over to where I can see I need to see my original system. So isn't this moment about A in the original, we're going to have our 100 is going to, the X component will not cause a moment, but the Y component will, right? So we have our X component that would go right through point A. That's not going to cause a moment. Our Y component will cause a moment. The 200 pounds, the X component and the Y component will cause a moment. And so if I take the 100 times the sine of 30, that's the Y component, that's going to cause a positive moment, and the moment arm is going to be 3 feet. For the 200, it's going to, let's look at our 200 times the cosine of 60. So we'll look at the X component first. That's going to cause a negative moment, and the moment arm is going to be 3 feet. And then we're going to have the y component, sine of 60, and that's going to cause a positive moment about point A, and the distance is going to be 5 feet. So I'm just taking moments about a point, right? I'm just finding what are the moments. I'm looking back over here at my original picture to come up with this equation. And then I've got this m of 50 foot-pounds plus 50 foot-pounds. I don't have to multiply it by distance because it's already in foot-pound units, and it's a couple moments. And so I just look and it's going counterclockwise, so it's positive. So I'm going to find my moment about A of the original is equal to, when I add it all up, 766.03 foot-pounds. So now I've got this value here for the moment about point A of my original. I can find the moment about point A of my equivalent, which is just a positive FRY times X. And I know I'm out of time here, but let me just finish this problem. If you got to run, you can come back and watch the video here. But our FR, so now we can set these equal to each other. So we just say 766.03 is equal to 223.21 times X. X is equal to 3.43 feet. Oh, what did I do? Cosine times, is the second line supposed to be minus 200 cosine 60 times 5 feet? No, it's 3 feet because it's my vertical distance on there. So let me get to a spot where I can see this. So if you got to run, sorry I went over a little bit there. Have a great rest of your Monday. We'll see you on Wednesday. And then let me answer this question and double check my math here. And if there's a correction, I'll let everybody know. But if I have this is my 200 cosine of 60, right? Is that one right there. And so how far is that line of action from A? It's that 3 foot distance right there. And then the 200 times a sine of 60, which is this one, that's where I use the full 5 feet. Okay, thanks for asking that question, Basil. Okay, so I think that finishes up. You all have a great rest of your Monday. We'll see you.